Hello there, my name is Mike, and welcome back to my channel. Today we are talking about something called a vector field. This is now the third part in our kind of discussion about vectors. This is a part of the Physics Foundations playlist where we teach ourselves physics from start to finish. And this is the last part, like I said, about vectors, so we can get into the fun of physics after this. But this is a really cool concept that I think you'll find just as interesting as I do. So a vector field is something we have not looked at before. We have looked at two-dimensional vectors, arrows in a plane. We've looked at three-dimensional vectors, the way in 3D space you might have something that points outwards into the screen at you. And now we're going to look at what happens if I wanted to describe the motion of, say, a fluid or the direction of a gravitational pull of a body. We can do this with something called a vector field. Here is an instance of a very simple vector function. So the way this works is it's a little different than a standard function. First of all, notice that we have a function of two variables, not just one like you're used to seeing. This is not f of x, it's f of x and y. Specifically, we have an f of x and y, and notice I have that arrow at the top. And as before, we've talked about, that arrow means we are dealing with a vector quantity. So this is a function that does not spit out a number like a normal function you may have seen. This is a function that spits out a vector. And the vector is governed by the x and y point that we choose. And it says that f of x and y is equal to x over 2 in the I hat direction plus y over 2 in the j hat direction. Now remember, I hat and j hat are these kind of fundamental unit vectors, these standard basis vectors for a space. Here's I hat, here's j hat goes up, I hat goes to the right, and they're each one fundamental unit of length in their respective axes. So what we're doing here is changing these coefficients, and it's going to create a certain shape. Let's go ahead and do a couple of these. The way we write these vector fields then is we need to get a bunch of points along this area here and actually write it out. So let's do that. Let's start with a couple simple ones. So the first one that I'm going to do here is it says we have x over 2, and again I wrote this again just as a vector itself, so this is the same thing just without the standard basis vectors. We're dealing with a vector function that's x over 2 and y over 2 for a given x and y. So we'll start with a point 0, 1, and 0 over 2 is of course 0, y over 2, or excuse me, 1 over 2 is 1/2. So we have a tiny little vector like that in the y direction. Let's do another one. We have over here, and let me write this out too so you can see what I'm doing. I'm saying f of, here's this point, this is the point 1, 0, is going to equal 1 over 2 and 0 over 2. I just plugged in the x and the y, which is equal to 1/2, 0, and I'm going to draw a little arrow like that. How about 1, 1? F of 1, 1 is going to be 1/2 and 1/2. Again, I'm just plugging in the 1 here and here. And if this was f of 2, 2, this would be 2 halves and 2 halves, which would be 1 and 1. So this is going to equal 1/2, 1/2. And that's going to be plugged in here as well. And it looks a bit like that. So notice how I have this tiny little arrow, and the arrow is now corresponding to the space that I exist at. And it does have a length, and you could figure that out. You could figure out the magnitude and calculate all of this. I will tell you now, as like a little cheat of information, normally when we do these vector fields, we don't really care too much about the specific length of the vectors. Sometimes that we do, sometimes they're very important, but a lot of times when we're writing out these vector fields, what we really care about are the directions of the field that it comes out. So I'm going to save you a little bit of trouble and tell you kind of preemptively that if you went and did this for all the points in the vector field, you would end up with something like this. Actually, this would come out here. This would come out here. You would end up with some sort of function that looked a bit like, make sure I put my points right here. This. And as you can see, there's this kind of thread where all of it comes out from this center point. And if you were to graph, say, a whole bunch of them, it would start to look like this. This is a vector field. And you might be able to make the case that, hey, maybe this is what the electromagnetic field of a charge looks like. It isn't, but just for now, let's pretend it is. I do want to give you a couple real-life examples of what a real vector field looks like. And so I want to show you two vector fields here. One is the vector field of a magnetic dipole, which is basically a single polarity magnet. Something like this guy right here. This is something I use to demagnetize and magnetize tools. But there is a set of magnets in here, and they do create a magnetic dipole field, and it looks something like this. So here we have a vector field, and again, we have a set of points here. We start at 0, 0. These are our x and y axes, and you can see there's a sort of shape that's made here. And if we were to trace these shapes out, you get something called a magnetic field line trace. So there's very useful physics that can be accomplished with vector fields. And I would say when working with, especially electromagnetism, 50-ish% of your job will be finding vector fields like this, or at least finding points along the vector field. And there are some very specific equations that we'll get into much later in this course that will give you the specific values of any single point in this vector field. And that's, as you can imagine, very useful information to know. The last vector field example that I can give you is one for gravitational the gravitational pull of an object, if I can find it in here for you. And the gravitational pull on an object is going to look something like this. Now, in this case, we used Newton's law of gravitation, which again, we'll actually get into relatively soon. And we've plugged it into three-dimensional space, and you can see that the magnitude of gravity gets much larger. The magnitude of the force is much larger near the surface of the object, and as you go further and further out, the pull is lessened, which is exactly what gravity does, and we have a term for that. It's called the inverse square law. I'm very excited to get into all of these, but the key to understanding vector fields is very simple, and it's to understand that all we do here is take a function of x and y, or some variables here. Sometimes you'll also see these as a function of r, which is a function of the radius of something. So we'd see f of r is equal to, and then we would do something to that r hat vector. And in that case, you could think of it like, a lot of these have symmetry around their axis. In fact, the field we saw for gravitation has a symmetry here. This is the same as this is the same as this. Any axis is similar, and if we were to go off kilter at any point here, we would find a line that starts small, and then the arrows get really, really big near the surface. So this is a field that is radially symmetric, right? Gravity doesn't really... You're not going to have more gravity if I go to the left of a planet than I do to the right. But all that matters is my distance from its core or its surface or its center. And that's what we see here. So we call this radial symmetry. And this can simplify things. When we do Newton's equation of gravitation and we wanted to do a vector field like this, we're not actually going to sit here and figure out the x and y. We are going to write it in terms of a common radius away from something, r hat. Anyways, I think that's most of it, though. Just understand that we take a function, we take values, and we plot arrows where the values are. And that's really all there is to it. You won't do too many vector fields by hand like this because they are very difficult to do. It takes a lot of time, but they are used very heavily in the field of, say, differential equations, which we'll get into a little bit, and they are an analytic way to solve a lot of very complicated problems in mathematics. Another example I'll give you is a vector field that's actually helical. So it has a spiral to it, and that looks something like this. And you can see that at the origin we have this small spiral, and it just goes out and becomes more and more continuous along these sort of circles, as you can see. I think that covers it, though. I just wanted to show you that, and in the next video we will get into the fun of physics, and I believe we can start on Newton's laws. So I'll see you in the next one. Thanks so much for watching, and do like and subscribe if you found this interesting. I'll see you in the next one. Peace.